Alright, so hello and welcome. Howdy. Gotta eat breakfast at some point, but having not eaten breakfast. I wanted to. Oh no! Let's change this to part 3, not part 2. So here we are. Part 3, expression add operator. Whew, I've been struggling through this problem and failing, but that's okay. It's alright. Just keep trying. You know, what are you gonna do? What are you gonna do? I mean, part of it is somewhat incorrect for me to not test and not accept that look commit is like the time limit bounds, because I kind of knew both of these things. I knew one, I didn't test enough, and two, that I didn't. Yeah, so this is not testing enough these ones, and then also time limit bounds. I saw both of those. I could have seen both of those ahead of time, so that's my fault. And that's really just, I was kind of impatient, I guess. All right, so I think we have a correct answer, but it's too slow. So one issue might just be that we are calculating too many redundant, making too many redundant calculations. So maybe we can just dump everything into a map and memoize from there. That might be possible. We could try it. Basically put this as the result, and it's just an integer. I think it's the index. So this is quite the I think we can memoize this in this way. Yeah, I think this will work. You can actually use an unordered map too for using integers. In fact, we don't even need to use we can use an array of these things, and num.size. Yeah, that works. Yes. I think that works. Yeah, we can actually memorize it in an array if we wanted to. Okay, so base cases. So auto key equal. Actually, it's just int. So if, and we could set these to. How do we test that we've already? I mean, we could set booleans. That's a thing too. I don't really know if there's a way I can do it simple. Yeah, it's fine. I mean, we do both. It's fine. It's a memo test. I like this is more general. This is a lot simpler, logically a lot simpler too. Just have to do something like this. I also think I should have done this a while ago too. Yeah. Okay, memo test of I equals false. Memo of I is going to be, I guess these will be just, I actually don't think we need to necessarily have anything in these. I mean, we can do, how do we do this? How do we do it on time? I'll read the problem in a minute. Let me just see if I can code this up first. What are we looking for here? I don't think it's actually going to be as helpful as we'd like it to be. Maybe it will be more helpful than I realize. I'm looking for. We can use the memo test. So we would say if memo test of A, then return memo of A. And then when you return elsewhere, you're going to say memo test of A equals true, and memo of A is equal to ret, and return ret. That's the memoization that we need to do. Now, one question is, yeah, I guess we build everything here, huh? Let's see if this works. It's still correct. Oh. And we just need to capture these things, so. Relatively easy to memorize. No, I was gonna say, I don't think this actually helps us memoizing at all. Just the way this is constructed, I don't think it really does much for us. Yeah. Yeah. I mean, it's unfortunate. Kind of unfortunate that we don't get the speed up that we're looking for. Yeah. Let's see. It's possible that I just made a mistake here, though. Oh, you know what? I did wrong. I forget to leave this open. How are we doing on time? All right, I'll read the problem in a moment here. Okay. Yeah. Okay. 192 milliseconds. So we memoized. We did. Memo test of A, memo of A. Set that to true. Return this. Yeah, the problem is that we're going right to left, so I mean, this makes things a little bit more efficient. Not much, though. Maybe run it a few times. Yeah, not really. Huh. We need to get through 20 of these tests rather than 3. Yeah, we TLE. Which one of these is this TLE on? I think it's the 0 that causes it to break. So it's interesting that it's like multiple test cases that it TLEs on. It's kind of peculiar. So that's interesting that so it seems like all 3 of these wouldn't. So that's interesting. So sometimes it does TLEs and sometimes it doesn't. That I wouldn't expect. I think it's kind of random. So yeah, so what's interesting about this is that we don't the memoization works. That's also really interesting. But it doesn't do anything. That's kind of what my point was before, is that memoizing is kind of meaningless here. We can do this in a way that's not a depth first search, or excuse me, it's still a depth first search, but it's not recursive. And I think that's the key. I think that's the trick, is that if we don't make it not recursive, then it'll be efficient enough. But sometimes doing this recursively is too expensive in terms of time, which is really annoying, but I guess it is what it is. So, All right, let's do. Let's try to write this in a way that's not recursive. It's basically the same code, but in sort of a written slightly differently. So we would do same idea. Let's do this. It's kind of like DP, but it's not really DP. I don't know how much more efficient it will be ultimately. I guess we'll find out. So, all right, we could start with num size, memo test. I don't really need that anymore. We can say we have this memo of n. Again, we're going to go right to left. We're going to say this loop. So we don't need this stuff anymore. It's going to be inlined. Do have a loop for int a. It's going to start from the right side, equals n. A is greater than or equal to 0. Decrement a. And for each of those values, we're going to do the following. Put that inside. Have a temp variable. You have this return variable, return value, long current p current I p c p times the character, increment temp, skip leading zeros. Our loop auto result is going to be f. We can do a reference. This could be instead of f of I minus 1, this is going to be memo of a minus 1. Oh, is that I minus 1 or a minus 1? It is I minus 1, memo of I minus 1. And then we're going to say const auto result, new operation, all this logic, push all these things back into ret, this new vector that we're creating, these tuples, and then we have base cases, secondary base case. If I makes it all the way through, if I doesn't, so actually I pretty much always makes it all the way through, so we don't really need that anymore. Yeah, this is always going to happen at the end. And we push back these values. Memo test, we don't need to do that anymore. We can do memo of a is equal to ret and return ret. Yeah, so now we are going to go left to right though again, which is interesting. So we're actually going to start from 0 and less than n and increment a. So it's interesting how you flip back and forth with recursion and going top down and bottom up and all of that. It's like different directions that you go. It's really kind of a curious thing. But when a is 0, we need to initialize that with, so I think what we're going to do probably also at the end here, you do one more operation. This is not DFS of no minus 1 DFS, but it's going to be probably memo of n, I think ultimately. Yeah, we're probably going to do this and make the initial memo of I minus 1 when I is 0. This is going to be greater than or equal to 1. And it's going to start off at A, right? And we're going to say when you're looking at memo of I minus 1, I think that's just empty. I think we do it that way. It's just an empty vector. So there's nothing to process in that scenario, that instance. Yeah, I think we'll do it that way. And then, so memo of 1 will have, yeah, we could do something like this. This would no longer be its own function. This is sort of just like the outer loop. Something like this ought to work. Just thinking, what else do we want to do? We do one more processing step at the end here. Now I guess one question is, everything gets copied each time here, which is kind of awkward. I think that's maybe something I shouldn't be doing. Like, I'm not sure if I should be using maybe I shouldn't be using a tuple here, but using a, excuse me. Maybe I shouldn't be using a tuple here, but maybe using something else so that the strings don't get copied over and over. Like, that might be another thing, an optimization going on here. Like, this should be a struct instead, and we shouldn't be doing all this copying each time. No, I think it does get copied actually. I think it's fine. I think it's supposed to do that. I'm thinking about it. Not really sure. So let's see. First, does this compile? Probably not. There's probably a few pieces here that I'm missing. Yeah. Oh, we don't return here. Don't return anymore. TLE. No. No. Huh. Okay. Try the test cases. TLE. Okay, that's probably just looping infinitely then. Wait, what? Why? I don't think it's looping infinitely. I think it's this test case that's causing issues. I think that's the problem. It's probably fine in the other test cases. No, it's wrong in the other test cases. Okay, that's interesting. Huh. Oh man. Takes a turn for the worst. Takes a turn for the worst. Interesting. Oh no. Okay. We're still going left to right here, but I starts off at A and drops down. A is 0, so I think we're not supposed to start with A as 1, or start with A as 0. That might be part of it. Okay. Alright, let's do 1, 2, 3, and 6. Let's just start with that one. So that I didn't think that was going to translate that well. And it didn't. Did not translate that well. So we get everything in I minus 1. And we get this value for ret. We take all of the smaller memoized results, so we update current, and we want to put current on the right side, or temp on the right side, current on the right side, Yeah, so this actually should work fine. Why, um, hmm. Hmm. So what's wrong? Oh, well this is now, yeah, so I think, oh, this is awkward. So this is still going right to left, but we need to reverse our memo. Yeah, okay, I see. So we want to go the other way around. we do want we want this to be I plus 1 over here now. So it'll be on the right side, moving to the left, and this will be memo 0 at the end. Okay, that's a little confusing, but I think it's okay. So, and A is going to start from N to greater than equal to 0, and decrement A. I think so. I think so. Something like this. That's what we're after. I don't know what happens when we do this. It gets really confusing from time to time with the nice. Gets confusing from time to time with like how it's supposed to work. Oh, so no. So not I plus 1. No, I and minus 1. Yeah, there we go. How about that? What does that do? Still wrong, but maybe better. So A is all the way on the right side. I starts at A. I goes all the way down, down to here. Let's see where that goes. No. Memo of I plus 1, which is the last thing we got on the right. No. So we're moving right to left, but we're processing. Oh, it's so confusing. Oh, that's great. Okay. I'm gonna just sit down for a while here and sit and ponder this here. Oh boy. So wrong. Why it's always so confusing going from the bottom up to the top down and vice versa. It's so much easier because it's sort of like the recursion part. I don't know, like the recursion part, you kind of always know what's happening, right? Because the function call you're making is an exact copy of excuse me, the original function. But with dynamic programming, it's like, I guess the thing you're referring to is supposed to be an exact copy also. So yeah, we do want to go in our loop. We want to go right to left. So that was correct. That was right. So that was starting from. So this part is fine. This inner part is fine. The tricky part is this: is it I plus 1 or I minus 1, and what do we do with A and memo? Because memo is just kind of like we could traverse memo any direction we want. Whichever one we need. We can go left to right, right to left, whatever. It's just data being saved into an array. So the trick is we want to process everything to the left side we want to use. So we actually do want I minus 1. That is what we want. We do want I minus 1. Excuse me. So that means we need to actually start A in the other direction in order to, so A does need to go in the other direction if we want I minus 1, right? Because I minus 1 is going to represent all of the processing we did on the left side so far. All right, we're going to kind of do this in pieces. Sure. So then, if that's the case, then where does I start in this inner loop, right? If memo of I minus 1 is to the left, that means we actually start from the right side. We start at 0, which is confusing, I realize. So this loop actually now has to go left to right, which is confusing because we're going to build the left solution as we go, left to right. Yeah. I don't know if that makes sense. I don't know if that works. Well, we could start with the whole word and or digit, like the whole expression, move left to right. So now it's going to be, this is kind of a curious thing, but this is going to be the whole integer. Just call it entire. And that's going to be, this is it's quite the thing here, huh? It's a character. So it's actually, we're going to do the most significant digits first. Yeah, so this is the entire thing plus c minus 0. Okay. And now we're actually going to take the entire thing and divide it by 10. It's a long, we'll call it current. We don't need p anymore. Current equals the entire thing divided by 10 raised to I, wherever I is starting at. So I actually is going to start at A. Still start at A. It's going to be A minus 1, I believe. So A is processing the first iteration. And we want the whole, potentially the entire sequence. So A minus 1. This is going to be from wherever I is. Oh, that's confusing. We divide by 10 to shift to the right. Yeah, it's integer division by powers of 10, depending on what I is. And then that can be another value here. We'll call that P. Starts off at 1. Multiply that by P. Increment P as well. The entire thing divided by, so when P is 1, the entire thing's divided by 1. When P is 2, or when the second iteration, when A is 2, P becomes 10. I think that's correct. That's a little more efficient. We do it that way. And then we can say, so we have this entire number. Hello, here to say hi, but I will go and make another video. See you later. I was here to greet you. Oh, I appreciate it. Thanks for coming by, Melito. I don't always check so frequently, but I appreciate it. I saw one of your videos earlier. So 3 elements of worship. That was good. I like that. Prayer, service, and sacrifice. Yeah, I was grateful for that. I thought that was good. That's good. But I don't know if you're still here. That was a couple minutes ago, but appreciate it. All right, so yeah, we got P, entire divided by P is the current value. We're gonna update P as we go. We're gonna have a new value for P. So what's interesting though is this is where you start, and then now the current value we're gonna divide by 10. So as we increment I, we're gonna say current divide equals 10. All right, that's the deal. And now we don't have to update current here anymore. Update the character, we don't really care. We do actually still want the character though. So part of the problem with this is oh no, this makes sense. I'm so sad. Oh, it's not working. No, no. Oh, this is so messy. I gotta like think through the solution before I start coding it. Yeah, it's too hard. It's too hard to like try to finagle your way through it. You really gotta have a sense of like what it is you're actually gonna code before you start coding it. Otherwise, then you just end up in this where I'm at right now, where I'm just like, wait a minute, these things don't make sense. How? I should read the problem again. I'll do that once I get this working. I'll read the problem again. How, okay, what are we doing? We want the. I don't even. Excuse me. What am I looking for here? We want. What do we want? We want. The. Excuse me. Okay, I'm here. I'm focused. Okay, part of the issue is we're gonna go left to right, processing the left side first. Left to right, processing the left side first. We're going to have a number, so we could start with the whole number and then progress in that direction. One of the issues is we start with the entire number. So that would be from right to left, I think, something like that. I don't know. I'm not doing this correctly. We want to process the entire left side first. And so the number we want, no, so I had it right the first time. We're gonna build the number right to left. But the issue is that we don't have the whole left side yet. So let's take like the first two steps, right? The first two iterations. Initially, we're gonna have an empty set. The first iteration, we're going to just end up with just the number alone, no operations on it. So we are still going to go right to left. So I actually had that. I shouldn't be rewriting this part. Had that right. But it is going to start at the value for A and move to the right, or move to the left rather, as we build the number. So a value of A minus 1, I think. And move right to left and build the number up. So I had that correct. And then the third iteration, right, or the third value, so A is, so memo of 2, right? Memo of 0 is just never gets touched. Memo of 1 we're going to use. And then memo of 2, what we end up with memo of 2 is, it should be, sorry, on 1, 2, 3, there should be a number 1 in memo of 1. and we process that with 2, and we have, you can add 2, subtract 2, or multiply by 2. And that's going to be what's placed into, should be memo of 2. And you also can have 12, right? Just 12, which is interesting. So you can do 2 and 1, or 12 and nothing, right? Or just 12. So that's, yes, that's what we want to do. Okay, so let's go all the way back. We don't need to, confusing myself here. We don't need this. This is memo of I minus 1. This is gonna go right to left, so we are gonna decrement I, but I is going to start at and yeah, it does end at 0. So I starts at a minus 1 though, right? So it starts at a minus 1. A starts off at 1. Memo, we are going to go left to right on A, and then right to left from I. Little confusing. A little confusing. What does this do though? What happens if we do this? Oh, this should be memo of N over here. Current, I think we set to 0 initially. That's what we had before. I don't remember what we had for current. I think it's just 0. Runtime error. I0. Oh, I see. So I will be at 1. Well, yeah, I will be a 1, and this is then I minus 1 here. That's confusing. So when we're looking at num of 0, we should be looking at memo of 0. Yeah, I guess. Yeah, I guess that makes sense. Something like that. In that case, though, oh yeah, that does make sense, because then when you get to, no, you don't get all the way through though. You run into issues if you do it this way. So this should loop. This actually should loop here. Part of the problem though is right where we're shifting things to the right slightly. So I think it actually will go like this then. Something like that. And then we actually want memo of N rather than 0. Oh, there we go. That works. Great. Ta-da! Just have to think that through. It's a little confusing. Yeah, okay. But we're still slow. I mean, that's, we're still pretty slow. Rather slow. I guess we gotta go through like 22 different test cases, 23 different test cases. I think we still TLE. Yeah. No. 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 Nope. Didn't work. Alright. That's frustrating. That's frustrating. So at least we don't need this part. I mean, we really don't need that, but it's not much faster doing it this way. That's awkward. Man. Well, how are we supposed to do this? I don't know, man. I don't know, man. Am I supposed to prune this? Is that the idea? You can't reach the target anymore. I mean, I think that's just the idea. I think we're supposed to prune this somehow. I don't know, man. Like how do you do that? How is that supposed to work? It's kind of all I got as far as what can be done here. I mean, you could maybe instead of using tuples, you could maybe update these pieces here. So, kind of doesn't matter, right? Because you would be creating each of these pieces anyway as you go. These triples. Yeah, I guess you'd have to prune this somehow. This is a brute force approach. I mean, this is about as brute force as it gets. Yeah. Building the associated strings as you go. Maybe you could do this another way that's recursive, I guess, another approach, which is what you can do is you can say, okay, take the first values that you could have from left to right and say, all right, what targets could I generate on the right side? And I either multiply this number by that, or add this number to that, or divide or subtract the other number from what I have, and get the target that we're looking for. That's kind of what I'm doing. That's kind of what we're doing. And then we can eliminate. Yeah, that's actually what we're doing. That is what we're doing. We're saying, process the whole thing, and then whatever strings evaluate, then we take them. Because you can't really, can't really prune these too well. Because you don't know what values you can get. Something like that. Like you have to process everything else to get part of the target, and then yeah, how could you prune any of this? I don't know. I don't know what you could do really. Just TLE over and over again. It's great. Great. Now, one idea you could do in theory is break up, instead of using tuples, you could break up the tuples into multiple arrays, or an array of structs, so to speak, so it's something like that. The problem with that, though, is it doesn't really help us all that much, because you still need to access. I'm wondering if this matters. If those things do anything. I don't think so. I don't really think so. Yeah, that doesn't help. Yeah, because we're kind of just copying things over and over again, over and over again. I want to say that if we could change this, maybe that'll speed things up a bit. Putting the character to the left. What does that do? Excuse me. Well, you'd have to reverse it each time anyway, so it doesn't matter. I'm trying to not do a quadratic amount of time building this string each time. It seems like that would speed things up a lot. If we could modify this string. The reason why we go left to right instead of right to left is that we want to the natural order of things for the addition and subtraction is left to right. It may be more efficient to go right to left, but then you need to do all the operations in kind of a haphazard way, like the addition, subtraction, and the multiplication. Maybe the way to do this is put just one addition, multiplication, addition, or subtraction between the, like in other words, do this recursively in ranges. So do kind of a divide and conquer type of thing, similar to that, where left side and the right side, you process those as ranges, and you get all kinds of different possible values, and then you put a multiplication symbol between the two. In another instance, you would have. Now the tricky thing about that is that there are no parentheses here, so we can't quite do it that way. It's fine with an addition. No, it actually doesn't work with an addition. Excuse me. Yeah, figuring out some way to kind of break this into sub-expressions. Like if you put a multiplication right in the middle and say, okay, what are all the values you could produce on the left side, all the values you could produce on the right side, and then take the Cartesian product of all the multiplications you could have there, and do things recursively that way. And that might be a little bit more efficient. You can memorize over the range values I and j. You know what we could do? We could pre-process the strings that need to be generated, and the numbers, and then just access those. That might be faster. Excuse me. Yeah, I think that's better. Because you end up doing a lot of extra work and all of these subroutines calculating these numbers. I think it's not a lot of extra work here. This part, it seems like it's not much. Maybe it's a little bit, but this part is definitely a lot. Yeah, so we can do pre-processing step. Maybe we'll just add some pre-processing step. Each range. String associated range. Okay. Alrighty. Okay. So for int I equals 0, I is less than n, int j equals 0. So this is going to be, this one's going to go the other direction. So I, j greater than or equal to 0, increment j. We're going to say free, or just not dp, temp array, let's say array, two-dimensional array of strings of n and n, and I guess n minus 1. N minus 1 doesn't need to be. And we say less than n, and we say, oh no, n and n, I'm sorry, that's fine, n and n is fine. So now what we say really is just a substring, although, oh, this is a string, yeah, okay, that's interesting. So yeah, it's just going to be array of ij is equal to num dot substring of, starts at I and goes back. Well, you can do the other way around. You could do k equals 1 to k is less than or equal to n. That's probably easier. And then you have I and j. So we want, it's really, that's really awkward. It's actually, yeah, this is a very awkward thing. So it's between I and j inclusive, where I is to the right of j, which is really confusing. Maybe it's better to do I is to the left of j. It's so confusing. Yeah, it's better just do I to j inclusive. Yeah, it's all right. It's fine. And so it's going to be I and k. And this is going to be k minus 1. Yeah. I mean, you could do, it's probably better just do this. Why make things so complicated? And it's going to be j minus I plus 1. Yeah. I don't know what I was just doing with k is 1 and well, j is going to start off at I. Yeah, that's why. Yeah, because j starts off at I now. And then k would be, yeah, these are a little bit different. These are a little different, right? K, if you did I and k, you'd have k minus 1, but k, yeah, it's confusing. These are different ways of setting up this array, right? If you use k equals 1 and k less than or equal to n, the problem with that is, yeah, they're different formulations, like they're different ways of doing this. I think if you do I and k, there's a translation between these. J does start off at I. It's triangular. Yes, that's true. Well, I said it's a quadratic number, yeah. or the matrix has a triangular shape to it. Yeah, oh, that's interesting. So this has a lot of empty strings in there, potentially. Whereas the other formulation doesn't have any empty strings in there. It's actually more compact usage of the um, memory. That's interesting. Is that true? No, it's not. No, they're both triangular. They both waste a lot of memory. Or half the memory. Not waste a lot, but half of it. Roughly half. How are they related to each other, though? They're pretty much the same thing, actually. They're almost the same. Yeah. Mm-hmm. No, they're the same thing. They're actually the same. I take it back. Yeah, it's just you'd have to do k minus 1 on the index. K is just the number of characters. I minus j plus 1 is also the same number of characters. So these are exactly the same. Yeah, these are actually the same. Um, yeah, so there's that. So there's that. Okay, they're not that different from each other. So okay, great. Anyway, instead of c plus temp, we could just set this to array of I and j. So so this is from the left side of is I, the right side is j. We're going from I to a. I believe it's actually a minus 1 would be the correct. Does that still give us the same answer? Let's take this one. Okay, no. No longer correct. J minus I plus 1 gives you. Well, I think it's just giving us the wrong. I think everything should be empty too. Everything that's not should be empty string. By the way. I think strings, yeah, so we just need to initialize those that way. But that's not just, that's not, this isn't the right expression here. So I is decreasing, right? I minus 1 and a minus, I think this is what we want, a minus 1, I minus 1, a minus 1. There we go, yeah, so, all right. Is that any faster than we had before? Maybe, I don't know. It's a slight optimization. No. Not at all. Not even remotely. Nope. Nope. Doesn't help us. Okay. No, sir. Not helpful. Not helpful at all. Okay. Can I maybe make this a pointer to a string? Temp is then pointing to this address. You can dereference temp. How about that? Does that help at all? I don't think so. I don't think so. I don't think so. No longer. It's probably not the right syntax too. Okay. Let's see what happens. Oh. Yeah, you gotta dereference everywhere here. Don't think this helps us very much, by the way. It just makes the code more complicated. Oh, it does make it faster. That's quite a bit faster. Hey, sweet. No, not faster at all. Really doesn't make a difference. Not really. Not really, no. Doesn't really help. No. It's great. It's not good. It's not good. Not good. Correct, but slow. Is this any better? So it was like 500, right? I don't think it matters. Oh. Oh. Apparently that was slower, doing it the way that I just did it, or potentially slower. I think you have to run like a bunch of tests, plethora. Yeah, no, it doesn't matter. It doesn't make it faster, slower. It's just. Did this get a lot of downvotes? No, it's got a lot of upvotes. Pre-processing step really doesn't matter. Nope. Nope. I think it's the pruning that we need to do. Is it even possible to make this faster? Am I just spinning my wheels here? I'm sure it has to be possible. It's just not obvious how to do that. Yeah, otherwise it wouldn't be solvable, right? Brother, this is a really obnoxious question, I have to say. I'm really annoyed. Really annoyed. Definitely annoyed. Yep. Definitely really annoyed. Oh boy. So, what do we do? What do we do? Okay. Why do you build me a buttercup? Don't take my heart. Don't break my heart. I'll just take it and break it. Don't break my heart. Why do you build me up? Ho! Ho! Maybe we'll have to make this part 3 and come back. So memoizing is useless. Useless. Was useless. Was useless. Was useless. It was useless. Huh. Well, that's not ideal. Excuse me. You know what we could do? Instead of looping through... Alright, so we want to somehow prune the steps in between, but how can we even do that? We're not working with parentheses at all, so that makes things a lot more challenging. I guess not really, maybe. So we can. Excuse me. We can do something where. Okay, let's say we call this subroutine. Just try that idea. Let's call the subroutine recursively. On the left side and the right side. We can get the possibilities on the right side for addition and subtraction, and then just say, hey, part of the problem though is, excuse me, part of the issue, part of the problem is the right side. I want to prune as much as we can. I think that's really what this comes down to. The right side is so we compute the left side first, right? I mean that's so tricky. We can put the iteration that we do at the end, we can speed that up by placing all these things into a hash set and checking to see that's also really awkward because we have to process the final step, so that doesn't. Yeah, it's like we need to calculate the entire expression before we can prune anything, which is very awkward. I want to say that there's a way to do that better. It's a way to prune some of these. I think if we do any kind of pruning, that will be in much better shape. Oh boy. Yes, it's kind of annoying. Maybe I'll come back to this. Okay, addition, left side and the right side. There's some expression. I guess that's fine. The addition and subtraction, left and right. I think it's okay. The multiplication gets a little bit complicated though because you need to process the multiplication first. So you can't just process the two sub-expressions and then multiply them. That won't work. What you're going to need to do excuse me, is you have to actually, if you're going to multiply, you've got to multiply the two numbers that are immediately, two immediate numbers, and then process that as a middle expression, and then process the two subranges on the left and the right. So, I mean, maybe you can process all the multiplicative terms first. So you can split the multiplicative terms and the additive and subtractive terms into two pieces. And so you get all these multiplicative terms, which changes the nature of the problem, I guess. Yeah. Can you do that? Huh. There are a lot of different ways you can multiply these things. I don't know, man. I don't know. I don't know. Yeah, the multiplication really makes things complicated, I have to say. If it was just addition and subtraction, we can probably solve this relatively easily, or a little bit more easily. With the multiplication, though, how do we process that in tandem, but also have this sort of the precedence operation always respected? Oh, who knows? Who knows? Who knows? Excuse me. Excuse me. So maybe you could say recurse on a range of values. And what you're going to do is select a position to insert an operation. And you can calculate, when you insert that operation, you're going to process the left side, process the right side, and then apply the operation between the two. And you can do this recursively. Right, and you're going to evaluate all the potential possibilities on the left side and all the potential possibilities on the right side. And you can dump them into unordered sets, and so you can quickly process the operation from the left and the right side. So you loop through all of the left side values and reverse the operation on the target, and see if that is present in the right side values, so you can process those a little bit more efficiently, potentially, hopefully, instead of taking the Cartesian product of all those things. However, with multiplication, you can't just process the left side and process the right side and then process the multiplication. You're going to need to take an arbitrary number of digits on the left side and an arbitrary number of digits on the right side, from right to left to right and right to left. And what you're going to do is you're going to process this middle number based off of those. So you're going to take those two numbers, multiply, and I guess, see, that's a tricky thing too, is I guess you would do both possibilities, right? So you do multiply on the left side or multiply on the right side, um, of this number. I guess what happens is the two numbers that you're so no it's that's the right idea actually. So you're gonna take an arbitrary number of numbers to the left side, an arbitrary number of numbers to the right side, and consider those to be part of the multiplication. Those two numbers. You multiply these two numbers, and you process that before you process the other two expressions. And so now you calculate those two sub-expressions with this number in between them, as opposed to adding and subtracting those two sub-expressions calculated totally independently. Now you're actually going to modify them slightly, and part of the issue is now you've got this number in between. You have a left side and a right side. Now what do? Do you add, subtract, multiply? What is the? What is the idea? Well, I guess technically you can repeat the multiplication on both sides, left and right, or not, or continue to add and subtract. So I don't know if that makes a lot of sense to do that. Doesn't sound too sensible. Problem being, also I need a nap. I need to eat. Cold, tired, hungry. Also, praise God. Praise God. How to do. Wow. Wow. Remember to stop howling. Alerts my neighbors and they think something's wrong with me. What am I doing here? Trying to find a way to prune. Yeah, because the problem you run into is the multiplication's really awkward. Yeah, I think that's part of the issue. The multiplication is very awkward, and I don't know how to handle that. So you multiply two numbers to get one, and then I guess the idea is that you're either adding or subtracting the left or the right side. Like you're inserting this number between two operators now. There's a left side in this number and a right side in this number. And yeah, you modified those ranges, that's fine. But the question becomes, how do you actually process that? So if you were to add, you can call that recursively on that sequence, that portion. And if you were to subtract, add on the left side, subtract on the left side, add on the right side, subtract on the left side, that gives you 4 different possibilities. But then you have, again, you have the multiplications again. Like you could multiply again as well, in which case you'd have to process those first again as well. Which I guess is
fine. You know, you could have sort of any number of multiplications you want, and then you'll end up with, yeah, you still just have four cases, right? You still have a multiplication, an addition, and a subtraction on the left and the right side. So I guess what you would do is, I don't actually know. I think also these things should be memoized too, and I'm thinking about it because you could end up with, like evaluating the same spot a few times. What about, I guess for each I and j, there's just an unordered set of tuples, or an unordered set of, well, it could be a map of the numbers and their associated strings. So it could be a number, target number is the key, and then all of the strings that evaluate to that number, the expressions. Yeah, I guess that's okay. I'm just wondering, like, how do we go through all of the different multiplications though? That's kind of weird. Huh. I think you could do that. You can do that left to right, potentially. Well, that gets really confusing. Yeah, because huh. Oh, I don't know now. I don't know. Okay, excuse me. Oh boy. Mm-hmm. So you can evaluate a multiplicative term from the left to right and just have like, there's like a whole bunch of different places you could put multiplication signs, and that all of those will just give you different numbers, right? And then I guess what you would do is then decide, okay, if at all you have an addition or subtraction on the right side, then you would recurse on the right side of that with same thing, starting with multiplicative terms, and part of the problem is that I think you actually do that iteratively. You can do that iteratively. So you would add or subtract whatever term that you generate from all these multiplications, and then similarly just continue, just keep going. Huh. That's interesting. So I guess you just have like a whole array of numbers that get created. Then you're going to add or subtract a bunch of numbers from those. Oh, this is so confusing. This is like. I think I gotta take a break. I think it's too much. I don't know, man. I don't know. I don't know. I want to say it's hard to gauge exactly how this ought to be done. The problem is we don't prune. Excuse me, not properly pruning here. Well, okay, we can create all of these different starting points, and then we either add or subtract from the next starting point, and depending on the addition or subtraction, that's going to be recursive. It ought to be recursive. We can dump all of the results of the recursion on the right side into a set, and depending on addition or subtraction that we're processing, we can prune that way. So whatever number we have, we call that alpha. If we're adding to alpha, then take the target minus alpha and check if beta is in the recursive set, or the sort of inductive hypothesis set. If it is, then we can pair those up. If it's not, then we can only pair those ones up. Actually, those you would use a direct map. So you wouldn't even, because there are a whole bunch of different possibilities, and you would prune off. You'd only select one really for that particular multiplicative arrangement. And that would be left to right. Now the inductive portion. Now what's tricky about the inductive part is the recursing on the right side from there. We see, that's the problem, is that we are just kind of presenting all of the different target results, or just all the results of all the possibilities altogether. We don't really have a target value that we're looking for in particular. So I suppose that's what you'd want to do, is given that particular multiplicative value, you would say that on the right side you're going to try to achieve that new target. So for each of the values you could produce, like, so if you take a particular breakpoint in between, split point on the left side, you take all the different multiplicative values you could have, and then evaluate for addition all of the right side, all of the evaluations you can get with that particular target for all those multiplicative values. And similarly, you perform the same sequence for subtraction. So for alpha plus beta, you would say beta needs to be target minus alpha. For alpha minus beta, beta needs to be I would guess it would be alpha minus beta equals target. So beta equals alpha minus target. So for subtraction, alpha is minus target, or the new target prime, I guess, would be alpha minus target. For when alpha plus beta equals target. Oh no, wait a second. Yeah. So it's alpha minus target and target minus alpha, right? So they're negations of each other for addition and subtraction. And then, yeah, so then I guess you would just recurse with a new target in mind, and that would automatically prune as desired, as needed. Now, that's all well and good, I suppose. That kind of rules out what we were saying before about using an unordered set and all of that, because now you actually just give the key directly to the recursion, and it'll only give you the results that result in that key, if there are any results at all. So then you would say, so you have addition, subtraction. Now that recursive, again, that recursive routine starts again left to right with all these different multiplicative terms. So loops over. And what's interesting is then, yeah, we just have an index then from left to right, and then we just operate on another index. And I guess you do have at each step all of the multiplicative values that could occur. Interesting. I don't know if it's valuable to pre-process all of that. Maybe not. It may not be. I don't think so. No, because you don't necessarily know what all those numbers are going to be ahead of time. I mean, this is another way to do it. Yeah. Kind of annoyed at the time limits for this problem because it just seems like no matter what you do with this problem, there's just going to be a ton of, you're just going to have a huge vector of strings at the end. I think it's a lot more efficient if we do it this way because we're going to end up pruning a lot of things out a lot more efficiently, a lot sooner. I suppose, I think, I don't know. Is there really a pruning step in between? Is it even possible? Well, you could say, you could have a limiting factor where you say, okay, if I multiplied everything on the right side, so I think the largest multiplicative term that you could have would be like 10 factorial, right? Oh, you know what? I think that's what I'm doing wrong. Oh, that is wrong. Okay. I see the problem. Yeah. Oh no. I didn't mean to rip this out of the headset. I think I see the issue. Okay. So, excuse me. Actually, I don't know. Yeah, I think I'll have to go back to this. 9 raised to the 10th. Alright. That was a million billion. Excuse me. So that's... Never mind. I was going to say all the possible numbers you can get. Probably the largest number you can get is all of these multiplied across. So if your target is 91, 91, and you get this here. 3 times 7 times 4 times 9. Excuse me. Oh, actually, it's not that big. Never mind. I don't know. I don't know how to bound these numbers. But these are all not. Excuse me. These are all 9s. It'd be pretty big. 9 times 9 times 9 times 9. That's still smaller than 9999 straight across. So actually, I think in every case, excuse me, the digit that you're looking at, excuse me, the value you're looking at across. Oh boy, whoa, where did these hiccups come from? The value that you're looking at, if you just evaluate left to right, is the largest that you can get. So if you had a number like this, and you want to get to 9191, you wouldn't be able to from here, right? And you could just stop there. You could terminate early. So I think that's probably the issue. Is I need to add a little more pruning, and it'll be a lot faster if we do that. Because this number, the difference between these two numbers, maybe if you add, but once you
once you get to, so you can use the absolute limit for the largest evaluation of whatever's to the right is just going to be the whole number taken as it is. Because if you add and subtract and all of that, you won't be able to exceed it. Now that may not be true in all cases. I think it's true in most cases, but not in all cases. Like if you have a bunch of leading zeros, multiplying the whole thing across gives you 0. Multiplying any part of it really gives you 0. Adding a 1 just gives you a 1. Yeah, 1,000 multiplied across, added across. So the largest value you can construe would be just the number at that point, like left to right. So it actually would be valuable to pre-process the numbers at each position. Excuse me, and autocomplete. Oh no. All right, we'll have to come back to this. I think that was what we were supposed to do with this problem. I don't think we were supposed to just brute force it the way that I thought. I think we were supposed to cleverly, excuse me, notice that there is an upper bound on the numbers that can be produced, the sequences, and prune based on that. And I think we can just go back to the code we already have and modify it and just say there may be an easier way to add this pruning, but the simplest thing is that like you won't be able to add you won't be able to add more than the whole number to the right, and you won't be able to subtract more than that. So once you get to 3, 4, 5, 6, 2, 3 here, there's no way to get to 91, 91 because the difference between this and this part is way above 91, 91. If you add this, is still above 91, 91, and then if you multiply, it's still above 91, 91. So if any of those three are true, then there's no way it's too big at that point. So, excuse me. Multiplying by this is not really something. So multiplying either takes you to 0 if we have some way we get 0 here, or so unless the target is 0, multiplying really, it's only gonna, if this is already larger, multiplying, unless you're multiplying by 0 and the target is 0, that's like the only case where this could bring it down. Excuse me, if it's already larger, then multiplying won't help you. If it's already larger, then adding is not going to help you. So the only thing you're really left with is checking if subtracting. So you just have to check if the target is 0, and there's a way to multiply 0 by 0 here, and then also just need to check if there's a way to subtract. Technically adding here, like you could finagle a way to get a very negative number, but the negative number, so you actually adding and subtracting, you do both. You just say if the absolute difference between this total value and this total value exceeds the target, then there's no way to get there. Because the largest value, you could technically add a negative value that's larger than any of the individual parts, but the largest value you'll be able to subtract is the whole thing. The largest value you'll be able to add is the whole thing. So you could argue something like, well, you could add a large negative number somehow, but the largest negative number you can get is going to be the whole thing anyway. So that's it. So you can use that to bound your recursion, I think, and that helps a bunch, or to prune the brute force, and that should help. One issue too is also, I think that's it. I think it's just add that a realization there. That's kind of annoying. That's like an intuition that if you didn't have that, you just wouldn't be able to solve the problem. And like that, I don't know. I mean, I guess it's fair to have stuff like that. I mean, they are supposed to be hard problems, but I have to say, like, being required to have some intuition that you wouldn't normally be aware of or know about to solve the problem at all is like really obnoxious, like extremely obnoxious. I don't know what to think of it all or make of it all. I think I'm just annoyed. I'm annoyed. It's got so many upvotes too. People really like this. We're gonna have to look at the discussion later and see like what did I miss exactly. But it's kind of typical of these questions though. There's always some kind of like trick or something that you just are not aware of. Also, wow, they have so many problems. They have 2100. I haven't even gotten through. I'm at like 300 right now. Not even 300. I have like thousands of problems to go through. And here we are, stuck on this one, spending hours upon hours upon hours trying to figure out why can't we solve it. I'm gonna be so irritated in the future, like where I'm trying to figure out the pruning, the intuition to prune the solution, the problem. Also, wow, dude, these hiccups are rough. What's going on? I need to eat something. All right, I'm gonna go. Just take a break. Take a break. Get some food. Try to do something about these hiccups. Thanks again for watching. I think that's the problem. I think I'm just not pruning. I don't think there's a way to really speed this up beyond pruning. I think I just have to somehow factor that into my solution here, and probably do want some pre-processing. I don't think this part's the pre-processing step. I think I need to do the this needs to be pre-processed, so that way I can evaluate, terminate early based off of like a chunk of like what's left over, I guess, and how far away we would be from the target, or close we are to the target at that point. I do think maybe I need to reevaluate how I'm computing things here, because there's this issue of like, I'm trying to go through the entire thing before I evaluate. And maybe what you can do is you can force an evaluation just to check if you need to prune, and then prune appropriately or not, and then otherwise can just continue iterating. You could do something like that. Probably could work. We'll figure that out later though. Alright, so thank you for watching. Talk to you soon. Have a good rest of your day. I don't know what I'm doing. I'm probably just gonna relax, try to get these hiccups out of here, get some food, and I don't know, come back to it. So yeah, thanks again. Talk to you soon. Take care.